You may ask, when do we have to use matrices? I'm going to answer this question based on my experience. And again, if you talk to other people within the R community, they may give you slightly different answers, or they may give you their own opinion. Based on the type of projects that I've been working with, typically my first answer would be, so you use matrices when doing matrix algebra operations. Perhaps right now, the most glamorous example would be when doing machine learning tasks, machine learning data analysis. So again, if you're going to be implementing, developing code for this, very likely you're going to be using R matrices. As a quick example, right? So let's consider a linear model. Don't worry if you haven't been introduced to linear models within machine learning or multivariate statistics. I'm just describing this example for those of you who already have been exposed to this. So say I have an output, let me call it Y, in terms of matrix notation. Let's say this guy has n elements as a vector, n rows, 1 column. And say I want to consider a theoretical model in which I have a matrix X. This is my matrix X with n rows and p columns. Here are the dimensions. And a vector of parameters beta, it's going to have p elements. And then there's also an error term, an error vector with n elements. This is theoretical. So if we use the classic estimation method, ordinary least squares, then the solution to the estimated parameters, beta hat, will require to do some matrix algebra. Again, don't worry if you haven't seen this before. This would be the solution in matrix format. Here I have a matrix product with a vector. And if you want to implement this in R, this is where you would need to use matrices and matrix operators and matrix functions. Perhaps another case in which you're going to use R matrices is when you have data tables. And again, I'm using the notion of data table in a more generic way, not so much within the R notation or the R connotation. So you may have, again, a rectangular array, a rectangular table containing values. If all these values are of the same type, again, say everything, either logical values or all integers or all doubles or all characters, then maybe it makes a lot of sense to implement this thing in an R matrix. So this is another example where you typically be using R matrices. Now, what about R arrays? I told you at the beginning of the video that I wanted to talk about matrices and arrays. Here, arrays in the sense of R, not so much in the sense of programming and computer science. There is some commonality, but if you look at the traditional definition of what an array is from the programming point of view, that's not really going to match the definition, the notion of an R array. The simplest type of array in R is a two-dimensional array. And this actually corresponds to the notion of an R matrix. So an R matrix, it's actually an array, a specific type of array because it has two dimensions. What are these two dimensions? Again, this is the number of rows and the number of columns. Those would be the two dimensions of an R matrix. You also have, in general, n-dimensional arrays. And the way I will be using these two terms, matrices and arrays, so if I use the word matrix, I implicitly denote the idea of a two-dimensional array. Personally, I prefer to use the word array just to refer generically to n-dimensional things. Here's an example in pictures of, let's consider a three-dimensional array, because this is easier to picture. What a three-dimensional array may look like is, let me start first with a two-dimensional array. For example, with 3 rows. So let's write that here, 3 rows, 4 columns. This would essentially be a matrix. But for a three-dimensional array, so we need an extra dimension. So that extra dimension, I could try to depict that with this idea. So another matrix behind the front one. So the green one is supposed to be another matrix. The blue one, it's another matrix. And let's say we have a black matrix behind the green one, again, containing the same dimensions, 4 columns and 3 rows. So here's what I want to depict. So in addition to the rows, in addition to the columns, you're gonna have another dimension. And let me just consider again these 3 matrices that we could call 3 slices. And together, right, so with 3 rows, 4 columns, 3 slices, that would give us 3, 4, 3, a vector of 3 dimensions for, again, a 3-dimensional array. Typically, when you work with arrays, 3-dimensional or higher dimensions, in mathematics, they tend to be called tensors. If you are familiar with this term, so here's the idea of n-dimensional arrays in R that are supposed to be the object in order to treat mathematical tensors. In order to create arrays, you use the array function. So again, as a generic, let's say 3-dimensional array, ARR for array, using the array function, I could pass an input vector, in this case, a numeric sequence from 1 to 8, and tell R that I want 2 rows, 2 columns, and 2 slices. And what this will produce, again in pictures, it's gonna be something like this. I'm gonna draw it like this so that you can see both slices. So the first one will be 1, 2, 3, 4, and then 5, 6, 7, 8. Again, so you would have the first row, second row, first column, second column. And then again, in a third dimension, you would have the first slice, that would be this guy here in the front. And the second guy, this is supposed to be in a second plane. This would be the second slice. Let me finish with a picture, a mental diagram of the things that we've seen so far. Starting with vectors. Again, I've been drawing vectors like this as contiguous cells of data, for example, 2, 4, 6, and 8. In this sense, in R, we tend to say something along the lines of vectors are one-dimensional objects, although from the technical point of view, vectors, they don't really have dimension, a dimension attribute, but just conceptually, it's just a one-dimensional object. Then we can take the next step, and again, from vectors, rearrange elements or build a tabular array with a matrix. A matrix has, as you know, 2 dimensions. So I could have, using the same numbers, 2, 4, 6, 8. And then more generally, well, I'm gonna need more dimensions, but let me recycle. Let's say we decide to recycle the input vector. So I could have one slice here, another slice here. They all containing the same things. And this would be 2 rows, 2 columns. And again, I'm gonna generically call them 2 slices. So a 3-dimensional array. All these guys are atomic objects. And again, remember the idea of atomic is that everything, all the elements inside either a vector or a matrix or an n-dimensional array have to be of the same type. Either everything logical, everything integer, everything double, or everything character. You cannot have an output that it's atomic, but at the same time, it stores different data types. They all have to be of the same data type.